Okay, it's time to look at exit slip 9 on the zeros of polynomials. In this exit slip, we were asked to use our knowledge of the rational roots theorem, or the rational zero theorem, to find the zeros of the function. So basically what that theorem tells us is it gives us a way to talk about possible zeros. So let's begin the problem by listing out our possible zeros, and then we'll use synthetic division to try out those possible zeros until we find zeros that actually work. So we're familiar with this P over Q idea, where P will involve factors of the constant term in the polynomial. So in our case here, we've got 24. So factors of 24 would be 1, 2, 3, 4, there's kind of a lot, right? 6, 8, 12, and 24. And I had to do plus or minus for all of those because we know, of course, we could multiply two negatives to get to a positive 24 as well. Now, Q in this problem refers to factors of the coefficient on the highest degree term, or in other words, it's factors of the leading coefficient. In our case here, the leading coefficient is just 1, so factors of 1 would be just plus or minus 1. So basically, our possible zeros truly are just all the numbers I wrote in the numerator because dividing by 1 doesn't change anything. So if you've worked on a couple of these problems before, you've probably discovered that the possible zeros list can at times be overwhelming, right? In this case, I'm just going to rewrite it without the denominator because we said that's unnecessary. But we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible zeros. That's a lot. But thankfully, the synthetic division process moves fairly quickly. Another idea that I know some of you are using, and it's not incorrect, we do have access to technology such as Desmos. Sometimes you can use technology to help you make a great first guess. So just a couple of ideas there. But let's go ahead and just plow through this one, as I'm guessing most of you did. So for the synthetic division, I'm just going to start trying some of these zeros. So let's say I try x equals positive 1. I'll just start going in the order of my list. And that means I'm going to put the placeholders coming from the function. So you can still see those are 1, -3, -10, and 24. I'm dividing by x equals 1. So I won't labor on this process too much, but I drop, I multiply, I add, I multiply, I add, I multiply, I add, and in this case our remainder is 12. So the remainder of 12 is no good in terms of this being a 0. So x equals 1 is not a 0. Okay, so if you're like me, you easily have a lot of scratch paper for your synthetic division. That's totally normal. Let's just keep plowing through our list of zeros. So the next in our list would have been -1. All right, so far we tried the +1. Now we're going to try the -1. Same thing, set up your synthetic division from the very beginning since the last one we tried did not work. And now I'll use -1 and we'll walk through that same synthetic division process. Just going to space these out a little bit so we don't get confused. All right, so again, I drop, I multiply, I add, I multiply, I add, I multiply, and now it looks like my remainder is 30, definitely not 0. So that means x equals -1 is unfortunately, again, not a 0. I want you to know that this process of getting not a 0 a couple times is totally normal. It doesn't mean you're a bad guesser. It doesn't mean you're doing anything wrong. It just means that there were a lot of possible zeros, so they all can't work out to be zeros, right? This was a degree 3 polynomial. That means there will be at most 3 rational zeros. Okay, next in our list was 2, so we just keep plotting along. X equals 2. So set up our synthetic division. Same beginning point, 1, -3, -10, 24. Now we're dividing by 2. So we'll drop and multiply and add and multiply and add and multiply, and hey, there it is. That is what we were wanting for. We were wanting a remainder of 0. So x equals 2 is a 0. So after our third try, right, in my case, we hit our first actual 0. And if it took you a couple more tries again, it's totally fine. There were 16 possible zeros, so we might not even have gotten that x equals 2 as a 0 on our third try, right? But it's at this point that I like to reassess where I am in the problem, right? It's exciting, we found a 0, but what does it mean in terms of our original polynomial? So to recap where we are, we began with that function, which I'll rewrite again. From the beginning of our exit slip, it was x cubed minus 3x squared minus 10x plus 24. And we did a little bit of work. We actually tried dividing by 3 different zeros. Only one of them was an actual 0. There were 3 possible zeros, only one worked. And if x equals 2 was the 0, right, we tried x equals 2 and that worked. That means the corresponding factor for the polynomial must be x minus 2, right? If you think about x minus 2 as a factor, setting that to 0 would give x equals 2. And when we divided by x equals 2, the remainder, right, this was a cubic to begin with, the remainder could be understood as a 1x squared minus a 1x minus 12. So I'll slip in that remainder. 1x squared minus 1x minus 12. So we now have a more factored form of the polynomial. It's not fully factored, so you have a couple options from here. Personally, I would like to look at this quadratic piece that remains and just ask myself if I can factor it. Another option would be to go back to the synthetic division, and continue dividing from where we left off. Either option works really just fine. I'm guessing a lot of you would probably be inclined to pick up with factoring at this point, so I'm going to show it that way. All I mean by that is I got to ask myself, I'm looking now for a way to break down x squared minus x minus 12. So of course x squared could come from x times x. And if this factors, it means I can find two numbers that multiply to negative 12. So multiply to the negative 12 and add to the negative 1. So as far as factors of negative 12 go, we have quite a few options. So I'll just list them out, because if you're ever stuck, listing them out will just help you find what you need. And I think that's it. So we have 6 different options there to multiply to a negative 12. Because of it being a negative 12, I had to take turns alternating one term being positive and one term being negative. So it looks like the pair in this list that adds to negative 1 in the middle like we need would be 3 and negative 4. So I'll use a plus 3 and a minus 4. By doing that last step of factoring, we now have a fully factored polynomial. And from there, it's very easy to tell now what our 3 zeros are. So let's just capture those 3 zeros. We already had kind of talked about the first 0 I see here, which is x equals 2. We found that through synthetic division. And now we see 2 more zeros of x equals negative 3 and x equals 4. So we get 3 distinct rational zeros. This was a degree 3 polynomial, so this is making some sense. So we get these as our 3 zeros. So the problem does ask us to do just a little bit more than that, and that is we want to use our knowledge of the zeros, which we just stated, combined with what we understand about end behavior to draw a sketch of the function. So let's comment on end behavior for just a moment. And I'm going to just transfer this information to the next screen. So if you think back to our first days talking about polynomials, we would ask ourselves 2 questions, right? We would say, what's the degree and what's the leading coefficient? And using our knowledge of just those 2 things, we could anticipate what the ends of the function would do. So the degree of this polynomial, again, it's easiest to find from the first line, is 3, because that's the highest power that we see. So 3 is the degree, and as we know, we really care more about is it odd or even. So 3 is odd. The leading coefficient in this polynomial would refer to basically the number in front of that x cubed term, so the coefficient on the highest power term. We can see in this problem that's just understood to be 1. And for the leading coefficient, we really care about is it positive or negative. So 1 is positive. So think back real quick on what you know about an odd degreed polynomial with a positive leading coefficient. And without too much trouble, or perhaps referring back to exit slip 8 a little bit, we'll remember that this means the ends of the function will look like this. Okay, so let's use this little end behavior sketch along with the 3 zeros, and we'll just produce a rough sketch of the graph. So we were asked to draw a sketch of the function. A sketch is not perfect, but it will give us a good understanding of the basic behavior of the graph. So I'm just going to slip it in right here so I can keep referring to the information we have on the screen. And I'm going to start, this would be my recommendation, start by putting in the zeros. So I know I have a 0 at x equals 2. That tells me the graph will touch the x-axis there. I've got a 0 at x equals -3, and I've got a 0 at x equals 4. So I just put those in right away. And maybe this is a good time to note that all 3 zeros have multiplicity of 1. So we've talked a little bit about this idea of multiplicity, because if the multiplicity is odd, the graph cuts through at those zeros. If the multiplicity is even, it will bounce. So because all of these factors are just to the first power, we understand each zero has just a multiplicity of 1. That tells me to actually cut through the function. So if I did not know the end behavior, then I would be stuck wondering, well, does that mean I cut through like this at the 0 of x equals -3? Or do I cut through like this, right? I wouldn't know for sure. But if I refer back to the end behavior, it tells me start the function, approach the first 0 by coming at it in this way. So I'm going to begin sketching my function by coming up from the base, right? So kind of like this. And I need to cut through that 0. And then if you want, maybe you tackle the far end next. So from my last 0, I need to just keep skyrocketing up. So that tells me from this last 0, I know I'm just going to keep shooting upwards. Now, I still got to fill in a little bit in between. The important thing to note, again, is that because of the multiplicity, I need to get back down to the second 0 and cut through it. So the only way I really see to do that is to let this guy go up and come down. There we go, we cut through. And then I got to connect my last 2 zeros. The only natural way to do that would be something like this. So what I've sketched here is, as I just said, a sketch. It's not perfect. I did not even label anything on my y-axis, and that's okay. It captures the zeros and the end behavior, and that's what we're looking for. So I hope that clarifies a little bit. I do agree and understand that this process is not the easiest, so hopefully the more we do it, the more comfortable it gets for us.